Okay, I wanted to explain the deformation homework that we have here. This is due on September 17th, at the beginning of class, so it's in 1 week. And it should be pretty straightforward if you've been paying attention in class, and you want to make sure to refer to Chapter 4 or Lecture 4. You remember this one, summary of measures of deformation of changes in lengths of lines. So remember the difference between extension or elongation and stretch. So make sure that's clear. And the first couple of examples here are looking at the sort of geologic scale elongation calculations. And so the first one here is one I chatted a bit about, and just want to make sure you can measure from one end to the other for your final length, and then you'll measure along the bed for the initial length. And you don't have to spend too much time on this. Just measure a bunch of line segments with your ruler and carry on, or you can even lay a piece of string along this layer, and you can get the L0, the initial length, really easily. So the first one is the sketch. The second one is a picture of this folded layer. I've tried to dash the center line of the folded layer just to make it a little bit easier. You can just do the center line itself. You can go a little bit further to the left if you want, but it seems possibly slightly confusing. The third one is one that's faulted and folded. So you're going to want to find a good marker within this layer and accumulate those lengths along the bed to get the initial length, sort of, let's say, along this boundary here, and then just, keep the final length calculation simple. And then the final one is kind of like the Hawaii example I had with the displacement vectors or velocity vectors. And so these are GPS measurements across the Salt Lake Valley. And so there's a lot of information, but you don't need too much of this information. Basically, the P09 station, as you can see at the bottom here, is moving to the east at minus 0.79 millimeters a year. In other words, it's moving west at 0.79. And if you compare P089 with P086, you see that it's moving west at 2.95 millimeters a year. So we see that there's an increase in velocity across the Salt Lake area, and that's because there's a big fault zone there called the Wasatch Fault. And we're just going to make this calculation for the easting component. So we just worry about the changes in east velocity and the east-west distance between the stations, even though we know there's a little bit of a north-south change. But let's just worry about the east-west part of the problem to keep it simple. So your assignment is to compute the east-west elongation rate. So remember, it's this is just divided by time, which is 1 year. So it's really about that change in length over that distance. So main thing is just make sure you keep track of your units, the conversion of kilometers to millimeters, and just work it through, following along with the example we had from Kilauea, if that makes sense. But remember that Kilauea, the velocities were moving toward each other, but the total distance was decreasing, whereas here the total distance is increasing.